Pre-calculus students, welcome to your 9.5 notes. Are you tired of living in a square world? Well, that's good because we're going to make things round today as we discuss polar coordinates and polar graphing. All right, so a polar coordinate is essentially just an alternate way of graphing things. They're in the order r, comma, theta, where r represents the directed distance. You might think of it as the radius from the origin O to a point P. Theta represents a directed angle counterclockwise from the axis to segment OP. Now in this little diagram I have here, it looks great. I probably could go ahead and mark R on here though, so I'm going to do that. There is R. It goes from O to P. That's the situation. So essentially, instead of thinking about how far, like when we graph in the Cartesian coordinate plane, the rectangular plane, we say how far right or left, and then how far up or down. Well, with polar, we think how far away from the middle in terms of the radius or r value, and then at what angle do we mark that point. So let's go ahead and do some graphing. These are pretty quick questions, honestly. 4 and pi over 4. So that tells me I'm going to have a radius of 4, 1, 2, 3, 4. And then I'm going to work my way around pi over 4 radians, which we know is right smack dab in the middle of the first quadrant. And there it is, 4 pi over 4. Okay, sometimes you could start with the radius and adjust. Some of you may prefer to think of it in terms of, well, where's negative 3 pi over 2? This is 0. This would be negative pi. This would be negative 3 pi over 2, so it's right here. And then you could count your radius from there. So if you're one that prefers to find the angle and then apply the radius, that's fine. That might really come in handy on a problem like number 3. 11 pi over 6 is over here, but we have a radius of negative 3, so we'd actually have to work our way back, and our point would end up being right out here in quadrant 2. So that's kind of an interesting way to think of it. We don't usually think of a radius as being a negative value, but it can work. All right, so question 4 says we want to represent the points in problems 1 through 3 in an alternate form. So we're going to take a look and see the graph and say, well, what's another way I could have described this? And I'm going to do these some different ways. Like on number 1, we could keep our radius of 4, but maybe instead of going this way, pi over 4, perhaps we could work the other way and call it negative 7 pi over 4. And I'm going to try to stay between, I'm not going to go crazy with coterminal angles here. I'm just going to kind of keep them within the first lap either direction around the circle. Here's 2 and negative 3 pi over 2. I think there's a pretty obvious way that we could graph this one. Well, instead of making it negative angle, let's make it positive. So we could call this 2 and pi over 2. Now some of you may have realized, hey, you know what, Hale, there's actually other ways, and you'd be exactly right. Like we could call this negative 2 and 3 pi over 2. That would actually work because 3 pi over 2 is down here. Negative 2 would mean I go that way instead. Or perhaps you'd realize like, hey, well, maybe instead of calling this angle down here negative 3 pi over, positive 3 pi over 2, maybe we could go the negative direction, make it negative 2, and then negative pi over 2. So there are basically 4 ways without even worrying about doing extra laps. Like, yeah, I could call this 2 and 5 pi over 2 or something like that, but that's not really what I'm trying to do here. I'm just trying to do some simple ways. All right, let's do this one. Negative 3 and 11 pi over 6. We're right over here. Now, you may realize probably the easiest way, in my opinion, would just be to make the radius positive. And we're going around 5 pi over 6 radians. So 3 and 5 pi over 6 would do the trick. All right, as we move forward here, we're going to be looking at some things we've already seen and we know, and then use them to do conversions. So we're really used to seeing sine of theta is y over r. We've studied that for quite some time. Cosine theta is x over r. But here are the two we really need to focus on. X is equal to r cosine theta, and y is equal to r sine theta. Those two things right there allow us to figure out a lot of things, like I can take a polar point and change it back into rectangular form, and so it would just simply look like this. Well, we know x is equal to r, which would be 2 times the cosine of the angle theta, which in this case is pi over 4. where y would be 2 times the sine of that angle, so 2 times the sine of pi over 4. We know that sine and cosine of pi over 4 are both square root of 2 over 2, so what we end up with is the ordered pair square root of 2, square root of 2. Pretty simple. All right, we can do the same thing. I mean, the next one, the r value is negative, but that doesn't change anything at all about what we're doing here. We're just simply going to follow that same procedure. X is equal to negative 1 times the cosine of 5 pi over 6. And then y would be negative 1 times the sine of 5 pi over 6. Again, you're seeing that x and cosine are connected, y and sine are connected, and we get the ordered pair. The cosine of 5 pi over 6 is negative square root of 3 over 2, but when it's multiplied by negative 1, that makes it a positive value, and then we'd get negative 1 half. Now, one thing you can always look at is, did I do this right? Well, think about this for a moment. Negative 1, 5 pi over 6. 5 pi over 6 is in quadrant 2, but the radius being negative would move us over to quadrant 4, and the point that we came up with is the equivalent form in rectangular is also in quadrant 4. That's a pretty good sign that we've done things well, and I believe we have. All right, now sometimes we get values that aren't exactly on the unit circle, at least not clearly specified on the unit circle, although they're there, they're just not written out, you know. And we can still use those, like 0.8 is our angle, okay? And by the way, you notice how it doesn't have a degree symbol right there? Lack of degree symbol equals radians, all right? Now in this one, since it's not a unit circle value, we'd have to go to the old calculator, and again, make sure you're in, of course, radian mode, or you could be in for a surprise when you punch those values in. They're not going to work real well. All right, so we're going to keep those relationships involved, or you know, those relationships in our mind, but we're going to move ahead and take a look at kind of working the other way. How do you take something that's rectangular and change it into polar? Two relationships for us to look at here. Tangent of theta is y over x, and r squared is equal to x squared plus y squared. I'm going to box those two things in. I think they're huge. We're going to use them a ton as we move forward here. So again, remember, polar form is r comma theta. So let's find r first. R squared is equal to 1 squared plus 0 squared. So we know then the r would be exactly 1. Tangent of theta would be the y value divided by the x value, and where that happens, where 0 divided by 1, that's exactly at 0, and that's radians or degrees, kind of your choice, take your pick. So the ordered pair there is 1 comma 0. Now there's one kid out there saying, oh, they're exactly the same. That's cool. Sorry, that one kid out there, you are, well, let's be nice about it, you're wrong. All right, so let's take a look at the next one. I can show you that they're not always going to be the same. R squared would be negative 1 squared plus the square root of 3 squared. This is 1, this is 3. Square root of 4 we know is 2. And then our angle, tangent of theta, would be square root of 3 over negative 1, which we could write as just negative square root of 3. Now, we have to pause for a moment, because one thing we got to consider is if you take the inverse tangent of negative square root of 3, that's actually going to take us to quadrant 4, which is fine in some cases, but if you look here, negative 1, positive square root of 3, that's quadrant 2 most definitely. So I need to use the quadrant 2 version here, and that would happen at exactly 2 pi over 3. And again, you can use your unit circle to see that. 2 pi over 3, the tangent of that angle would be negative square root of 3. And then our polar form of that point, negative 1 square root of 3, is 2 and 2 pi over 3. All right, one more for us to look at. And by the way, on any of these, there's more than one correct answer. I'm going to the ones that I would imagine you would use, but you could possibly use like a negative radius, I guess, if you really wanted to complicate your life a little bit. All right, so let's look at this one, 2 and 2. Now, if you're really thinking about this one, you might be able to figure it out without having to go through some of the calculations I do. Think about where 2 ends up. Which quadrant and where? All right, so let's start with this. The radius squared would be 2 squared plus 2 squared. So the radius here would be exactly the square root of 8. Our angle that we would use for theta, tangent of theta, is 2 over 2, which is 1. That's right in the middle of the first quadrant, pi over 4, and that makes sense that 2 and 2 would be in the middle of the first quadrant. So our ordered pair is r comma theta, and in this case that would be square root of 8 and pi over 4. Up next, we're going to look at taking equations both in rectangular form and in polar form and then switching them around, all right? So some of these you have to be a little creative. I'll just warn you up front. Some of them are pretty straightforward though. Like number 11, it says x squared plus y squared equals 25. Well, we saw earlier we have a relationship for x squared plus y squared. We know that's equal to r squared. So let's just write r squared equals 25. And hey, if we're solving for an equation, we might as well just go ahead and write it as r equals 5. Now, a couple things to point out. One, x squared plus y squared equals, we know that's a circle, right? X squared plus y squared equals 25. That's a circle with radius of 5. Well, what do you know? Right here, r equals 5. That makes sense. Another thing I want to point out is, I had r squared equals 25. Algebraically, you'd think, there's got to be a plus or minus right there. I get it, but when you think about it, r equals 5 or r equals negative 5 in polar form, try graphing them. They're going to look exactly the same. It's the same thing, all right? So when you see r equals 5, that means it's just a circle with radius 5. All right, here's our next one, y equals 3x. Now we're going to have to use a little bit more work to get through this one. One thing I know about y is that it's the same as r times the sine of theta. And I know that x is r times the cosine of theta. Now, what I would suggest doing is, first of all, writing legibly, but secondly, let's get the 3 by itself, which I know sounds kind of weird. It's not that I like 3 being by itself, but I like dividing both sides because you'll notice that the r's cancel. And what's sine of theta over cosine theta? Well, that's tangent of theta. And tangent of theta equals 3. Now, this is an interesting thing. Tangent of theta equals 3. Well, folks, if you graph y equals 3x, we know that's a line that has a slope of 3. It goes through the origin. You know what that looks like. Try graphing tangent of theta equals 3 on your calculator or on your Desmos machine. It'll work great on this. By the way, though, I should point out, if you want to graph these in polar form, like tangent of theta equals 3, you're going to actually have some issues on the graphing calculator. You would need to use that on Desmos. You can graph r equals 5. So anytime we have an r equals equation, we can graph it on our 84s. Anytime we have a tangent of theta equals, it's a little tougher. Probably would want to use Desmos on those. So I'm a big fan of Desmos, as you know, and in this problem, it works great. All right, number 13, a little bit of work to do here. Now, the first thing I see, x squared plus y squared, I know that's r squared, so I'm going to go ahead and change that right now. That's r squared squared equals 16. Now, I can't do a ton with x squared, but I could do this. I could make it r cosine theta quantity squared, put a bracket around there, minus, and then our y squared, we could make it r sine theta quantity squared. And it might be kind of weird to think, what am I trying to accomplish here? And I get that. But let's just watch what happens. So we know the r to the fourth then is equal to 16. These will both have an r squared term in them, so I'm going to factor that out. And what I'll have left is cosine squared theta minus sine squared theta. Now this problem may seem a bit more obscure to some of you because you may not catch this immediately. But folks, if you look on those golden unit circles you have, you'll find some golden information in that. You know that the cosine squared theta minus sine squared theta is exactly the same as the cosine of 2 theta. We had 3 forms to write cosine of 2 theta, our double angle. That's one of them. And then the other step we would do, we could go ahead and divide by r to the second, and we'd have r squared equals 16 times the cosine of 2 theta. And then probably if we'd want to graph this on our calculators, we'd go ahead and do this, take the square root of both sides. R is 4 times the square root of the cosine of 2 theta. And then I guess you could ask yourself the question of, what does it mean to do the square root of cosine 2 theta? And that's kind of a weird thing to explain. So I'm not going to get into that right now. But go ahead, graph it. Take a look at it. Graph it on your 84, graph it on your Desmos. Your call. And now to our last slide. This time we're going to work the opposite direction where we take something that's in polar form and convert it to the probably more familiar to you rectangular form. All right, now we don't have anything where we can take r equals 7 and directly convert it. We don't know it. We don't have an equation for r, but we do know that r squared is equal to something. So let's do this. Let's do r squared equals 49. I'm squaring both sides of the equation. And hey, we know r squared is the same as x squared plus y squared. So x squared plus y squared equals 49. That's a rectangular form. We can work with that, okay? And it's a circle, right? Radius 7. We knew that. Now, the next two might look pretty similar. They kind of are. But I wanted to show you because you run into different things. Sometimes you just have theta equals, and here's what we typically would do. It would say tangent of theta equals tangent of 4 pi over 3. I'm choosing the tangent function on purpose, and it has to do with the fact that we know tangent of theta is equal to y over x. It allows us to go directly to x's and y's. It gets rid of all the r's in one step, and it'll get rid of the thetas too. So in this particular problem, that works out pretty well. Tangent of theta is y over x. The tangent of 4 pi over 3 is square root of 3, and then we could quickly go ahead and just change that to be y equals x times the square root of 3. Hey, I like that. That's a line. It has a slope of square root of 3. It goes through the origin. Simple. All right, now let's take a look at the next one because we're running into something a little weird. If we try to do that same process, I'll do tangent of theta is equal to the tangent of 3 pi over 2. So, whoa, what's going on here? Did you see it? Tangent of 3 pi over 2, that's undefined. That's not going to be the best approach. All right, let me show you two ways we could do this. One is a bit just thinking about the situation. Where is 3 pi over 2? Well, that's at the bottom of the unit circle. So if I went from the origin to the bottom of the unit circle, I'm drawing a vertical line. Folks, that's your equation. It's a vertical line. All right, let me show you an alternate way if you're really into the algebra stuff. Maybe we could do a cotangent instead of doing a tangent, because I know at 3 pi over 2, the cotangent function, well, it's actually defined. And we know cotangent is x over y, so that's get rid of all the r's and the thetas and just giving us x's and y's. We like those. Cotangent of 3 pi over 2 would be exactly 0, and if you multiplied both sides by y, we'd have x equals 0. All right, so it's kind of a strange one, but you're going to run into it, so I wanted to show you. I think there are a couple ways, the visual or thinking way, and then there's the algebraic way where you could approach it. All right, we have two more. Both of these present some different challenges. Let's look at number 17. I'm going to rewrite this cosecant to be 5 over the sine of theta, so I'm just changing cosecant to its reciprocal function. And hey, I don't like the fractions, so let's get sine of theta to the other side with some multiplication. And whoa, what just happened here? Are you seeing it? What's r sine of theta? Yeah, you're right. Yeah, that's it. It's 5. That worked out pretty nice, didn't it? Okay, now some of them work out real nicely and quickly like that. Others take a little more work. I would classify 18 as one of those. What I want to do is, again, I want to get rid of the fraction. So I'm going to multiply both sides by 1 minus sine of theta. So I'm going to have r minus r sine theta equals 5. Now, this accomplished one really good thing, but it didn't fix an issue. Okay, so right now I'm still in polar form, but I know r sine of theta is exactly the same as y. Now we're kind of in this really strange, like, kind of mathematical purgatory of, like, I have portions that are rectangular and I have portions that are polar, and we need to decide which way we're going to go. So what we're going to do is we're going to move that y over there. And again, we know we can't really do much with an r, but we can do something with an r squared. So let's square both sides. Y squared plus 10y plus 25. And then my next step, I'm going to work up here. I know that r squared is x squared plus y squared. And I'm going to just rewrite what I already had for the right hand side. And usually with this kind of a thing, we can't simplify a whole lot. We can get rid of y squareds, but typically we put it in what's called a general form, where I'm just going to move everything over to one side. So I'm going to have x squared minus 10y minus 25 equals 0. Okay, really interesting one to look at. Kind of a cool problem, presents some challenges. And again, guys, if you're wondering, did I do these right? Try graphing them. You go on your Desmos machine, you can graph these in rectangular form, and then in the next line, graph something in polar and see what it looks like. See if you've done it right. Hey, I hope as we've studied these polar coordinates, you've started to understand how things go around in this, and come to class ready to work. We'll see you later.